Hello friends, I welcome all of you in second lecture on Riemann integral. In previous lecture we have studied the concept of length of interval and then set of measure 0. A subset E of R1 is said to be set of measure 0 if E is covered by finite or countable number of open intervals whose lengths add up to be less than epsilon. And then we proved that every singleton set is of measure 0, then countable set is of measure 0, then countable union of sets of measure 0 is again of measure 0, and empty set is also of measure 0, no doubt about it. Okay. In fact, there are uncountable subsets which are of measure 0. Okay. So example of uncountable set which is of measure 0. Uncountable set. So Cantor set is uncountable set with measure 0. And then set which is equivalent to Cantor set, that sets are again of measure zeros. Okay. So what is the Cantor set? By using the Google, you can search what is the Cantor set and how it is of measure 0. So try to find its solution by Google. Okay, that is exercise for you. Now I am going to explain the concept property hold almost everywhere, and for that we have defined the concept of set of measure 0. Okay, definition: let Px be property Px be property defined for x belongs to R1 or x belongs to some subset. Say x belongs to A subset of R1, then Px hold almost everywhere. Px hold almost everywhere, almost every point in A if E is equal to set of those x belongs to A where Px fail is of measure 0. Is of measure 0. This is definition of property hold almost everywhere. Property hold almost everywhere. For example, a function fx is continuous almost everywhere. For example, a function f from A to R is continuous almost everywhere. Continuous almost everywhere. This is abbreviation for almost everywhere on AB. If E is equal to set of those x belongs to AB where f is discontinuous at x. Discontinuous at x is of measure 0. Is of measure 0. Right? This is the definition of function is continuous almost everywhere. Set up those points at which property fail. So we are checking whether function is continuous. So we have to find all those points at which function is discontinuous. If it is of measure 0, then we say that f is continuous almost everywhere. Okay. Example: let psi be characteristic function function of set A is equal to say 0, 1 by 10, 2 by 10, dot dot etc. up to 10 by 10, subset of R1. Psi A is F continuous almost everywhere on 0, 1. Right. So solution here, A is equal to 0, 1 by 10, 2 by 10 and so on, dot dot up to 10 by 10 is subset of 0, 1. Psi A is characteristic function of function of A, which is defined as psi x is equal to 1 if x belongs to A and it is 0 if x belongs to A complement, but it is 0, 1 minus A, because we are just talking about characteristic function defined on 0, 1. Okay, not on whole real line, So if you plot the graph of this function, okay, graph of psi, so this is 0, 1, okay, 1 by 10, 2 by 10, 3 by 10, 4 by 10 and so on, 10 by 10 is equal to 1. So it takes one value for x is equal to A. So it takes 1 here, then here, 1 and so on. It takes one value here. Then it takes 0 value on open interval of 0 to 1 by 10. Then it takes 0 value on 1 by 10 to 2 by 10 and so on. So from graph, clearly function is only discontinuous at points in A. There are jumps. Okay. So graphically, psi x is discontinuous at. Graphically, psi is only discontinuous at every point in A. Now since A is finite, therefore measure A is 0. Moreover, A is finite and hence measure A is equal to 0. Therefore, psi A is continuous almost everywhere on 0, 1. Psi is continuous almost everywhere on 0, 1. So set of those points at which function is discontinuous is A, which is finite set, which is of measure 0, which is of measure 0, and therefore this psi a function is continuous almost everywhere on 0, 1. Is it clear? If I take next example, so let fx is equal to f from close interval 0, 1, or fx is equal to sine of 1 by x for 0 less than x less equal 1, and it is 0 if x is 0. We know f theta, we know trigonometric function sin theta, trigonometric function sin theta is continuous on, is continuous, or if I take x here on R1, and hence on 0, 1. Moreover, 1 by x is defined and continuous on open close interval 0, 1. Okay, here also on close interval 0, 1. Therefore, by chain rule, sine of 1 by x is continuous on open close interval 0, 1. And therefore, set of discontinuities of f, set of discontinuities of f is equal to E is equal to phi or singleton 0 in 0, 1. Okay. Where measure phi is equal to measure of singleton 0 is 0, and therefore f is continuous almost everywhere on close interval 0, 1. So here I have not checked whether sin 1 by x is discontinuous at 0 or not. I know that sin 1 by x is continuous everywhere except 0. It remains to check continuity of that f at 0. So if you are unable to check the continuity of f at finitely many points, then that points may be points of continuity or discontinuity. So set of discontinuity is subset of that finite set or countable set, and we know that countable set is of measure 0, its any subset must be of measure 0. So by that, set of discontinuities, it may be phi or singleton set, it must be of measure 0. It must be of measure 0. Is it clear? And therefore f is continuous almost everywhere. Here function fx equal to sin 1 by x is discontinuous at 0. By sequential limit theorem, limit x tends to 0 of sin 1 by x doesn't exist, that we have verified in metric space course. Is it clear? So this is about this one. Now I am giving one exercise to you. Let psi be characteristic function of set of rational numbers, set of rationals in 0, 1, so that psi is not continuous, almost everywhere. Okay. So by definition of characteristic function, what is your psi x? Psi x is 1 if x is rational. X is rational in 0, 1. And it is 0 if x is irrational. X is irrational in 0, 1. Then psi is discontinuous. Psi is discontinuous at every point in closed interval 0, 1. You have studied this example in FYBSC also, then metric spaces also. Okay. So it is discontinuous at every point in 0, 1, and measure of closed interval 0, 1 is equal to length of closed interval 0, 1, which is 1 greater than 0. Therefore, f is not continuous, or psi is not continuous almost everywhere in 0, 1. So if I take say psi x is 1 if x is in Cantor set is subset of 0, 1, and it is 0 if x is in its complement, then you can check that characteristic function of rational Cantor set is continuous almost everywhere. Where that function is discontinuous, that function is continuous at every point in its complement, and discontinuous at rationals, discontinuous at every point in Cantor set, and that Cantor set is of measure 0. And therefore that function will become continuous almost everywhere on closed interval 0, 1. If I talk about the characteristic function of Cantor set in closed interval 0, 1, so it will become continuous almost everywhere, no doubt about it. Okay. So with this discussion, we'll stop our this second lecture here. In next lecture, we'll develop the concept of Riemann integral, and for necessary and sufficient condition we require the set of measure 0, means for function must be continuous almost equal property for Riemann integrability, and for that purpose set of measure 0 is very important concept for us. So with this discussion we'll stop here. Thanks for listening lecture carefully. If you like the lecture, subscribe channel and do like for the lecture. Bye bye.